Namaste students. I am JVN Dr. Surendra Kumar Srivastava from the Department of Science and Technology under under the Faculty of Education and Methodology, JAYOTI VIDYAPEETH Women's University, Jaipur. Today, I will discuss the theory of subgroups. What is the meaning of subgroup? As by some previous lectures, we have studied about the group. What is the meaning of group? Actually, a non-empty set G with the operation O, which is defined on G, is called a group if the four properties are satisfied. These four properties are closure properties, associative properties, existence of identity, and existence of inverse. This was the definition of group. Now, what is the meaning of the subgroup? G is generally denoted by G, means group, and the subgroup is denoted by H. Now, a non-empty subset H of G is said to be subgroup if H is itself a group. It means H will also the following four properties, same as the group under the same operation. Then H is called the subgroup. Now we share some slides. See here, what is the meaning of subgroup? Any non-empty subset H of a group G, O is called a subgroup of G, O if and only if first H is stable for the operation O and H, O is a group. An alternate definition of subgroup. A non-empty subset H of a group G is a subgroup of G if H is itself a group with respect to the same operation which is defined on G. Now we will talk what is the improper or trivial subgroup of G and what is the meaning of proper or non-trivial subgroup of G. Subgroup of G means G and the identity. G and a set which contains only the identity element. This is the two subgroups are called the improper, and the proper subgroup, any subgroup other than these two subgroups, that is G and E, is called the proper or non-trivial subgroups. Proper means all the subgroups but leaving the trivial means G, E improper. The rather than the improper subgroups of G is called the proper or non-trivial subgroup of G. Now, some results on the subgroups are some theorems on subgroup. Theorem: a non-empty subset H of a group G is a subgroup of G if and only if A, B belongs to H. That implies AB belongs to H. And the second, A belongs to H. That implies A inverse belongs to H. Where A inverse is the inverse of A in G. Now see this line, G is the group and H is the subset. We have to show if H is the subset of G, then the following two properties will be satisfied. And because here if and only if, it means reverse will also true, means if anywhere H satisfied the following properties, then H will be the subset. Now for proof, let H be a non-empty subgroup of a group G, then first and seconds are fourths, means first we are suppose that H is a non-empty subgroup of G and first and second property are satisfied, and we have to show H is subgroup of G. For this we must show that H is a group Why we are saying we shall show the following properties? Because by the definition of subgroup, if H is a subgroup, then H must be a group itself. Then in this regarding, the first property is closure property for all A comma B belongs to H. That implies AB belongs to H by virtue of the properties. Now associativity A, B, C is equal to A operation B operation C for all values A comma B comma C belongs to H. Now see that A comma B comma C belongs to H. It means A, B, C will also belongs to G because H is the subset of G. Now G is the group, so associativity will be holds. That implies A operation B operation C is equal to A operation B operation C. This is the associativity in G. So associativity will also holds in H for the elements A comma B comma C belongs to H. Now the existence of identity. Let E is the identity element in G, then E is also the identity for H. That implies A belongs to H. That implies A inverse also belongs to H. This is by the second condition. Now A belongs to H and A inverse also belongs to H. Then by the closure we can write A operation A inverse that is equal to E will also belongs to H by first. So that implies E belongs to H. Thus identity element E belongs to H. So we can say identity property is also satisfied. Now we will talk on the existence of inverse. Each element of H is inverse will by virtue of second. The above facts prove that H is the subgroup. Now conversely part, now we show let H is the subgroup of G and we have to prove that the condition first and second are four. By our assumption, H is group. If H is group, then it will be satisfied by the closure and inverse property. Then the given conditions holds. It means it means if H is a subgroup of G, then it will be satisfied by the two properties, that is A comma B belongs to G, and the second property is A belongs to G, that implies A inverse will also belongs to G. Then and if H already satisfied these properties, then H will also be subgroup. This is the reversal of this theorem. Now for the next remark, a non-empty subset H of a group G comma plus is a subgroup of G if and only if A comma B belongs to H. That implies A plus B will also belongs to H, and A belongs to H. That implies minus A belongs to H. Here A inverse is equal to minus A. This is the remark for the operation if operation is addition. Now the next theorem, see the necessary and sufficient condition for a non-empty subset H of a finite group G to be a subgroup is that A belongs to H, comma B belongs to H. That implies AB belongs to H. This test is known as the one-step test. It means if we have to show the given group, the given set H is the subset of H and H is the subset of G, then only we have to show A, A belongs to G, comma B belongs to G. That implies AB belongs to H. This is called the one-step test for examine H is the subgroup of G or not. Now, again, we are sharing some theorem for proving. Now, It is also since if and only if. Then first we consider H is a non-empty subset of H. H is a non-empty subset of G, and then we will show A belongs to H and B belongs to H. That implies AB belongs to H. Given H is the non-empty subset of a finite group G such that H is a group subgroup, we have to show A comma B belongs to H. That implies AB belongs to H. Now H is a subgroup of G. That implies H is a group. That implies H is closed with respect to the multiplication. That implies A comma B belongs to H. That implies AB belongs to H. Given, suppose that H is a non-empty subset of a finite group G such that A comma B belongs to H. That implies AB belongs to H. Our aim to show that H is a subgroup of G. For this, we have to prove H is a group. We show closure, existence of identity, and the other properties. For the closure, there for all A comma B belongs to H. That implies AB belongs to H. It is given, so closure property holds. Now, existence of identity element. Let E be the identity of G for all A belongs to H. That implies A belongs to G. That implies order of A is finite, that is n. That implies G is a finite group, so every element of G is of finite order. That implies order of A is equal to n. That implies A to the power n is equal to E. It means here is theorem is also introduced, that is, if G is a finite group, then every element of G will contains the finite order. What is the finite group and what is the order of the element, what is the order of the group, will be discussed in the next video. Now A comma A belongs to H. That implies A square is equal to A dot A for all H. That implies A square belongs to H. Now since A square belongs to H and A will also belongs to H, that implies A cube will also belongs to H, because by the closure property. Repeating this process, we find that E is equal to A to the power n belongs to H. That implies E belongs to H. So identity element E will also be the part of H. Now associativity. Then A operation B operation C is equal to A operation B operation C for all values A, B, C belongs to H. So associative property also holds. Now we will talk on the existence of inverse. Let A belongs to H such that order of A is equal to n. Order of A is equal to n, it means A to the power n is equal to the identity element where n is the smallest integer. By the give positive integers, by the given condition A belongs to H, comma A belongs to H, that implies A square will also belongs to H, and repeating this process, we find that A cube belongs to H and A to the power n minus 1 also belongs to H. But if A to the power n minus 1 can be written as A to the power n into A to the power minus 1, that implies A to the power n can be written as E and A inverse will be the same. So E is the identity element which is already belongs in H. A inverse also belongs to H. That implies A inverse. And A to the power n minus 1 belongs to H. That is A inverse also belongs to H. This shows that for all A belongs to H, that implies A inverse also belongs to H. Hence, every element of H is inversible. So H is a group. Now, what type of questions will be imposed by this article? Subgroup. Then, what is the definition of subgroup and what is the one-step test? Or directly it is given in the form of prove that the given set, the given subset H is a subgroup if A belongs to B and B belongs to G, that is AB belongs to H. Thank you.